Hello, my name is Finnegan Wilson. I am a second-year mechanical engineering undergraduate student at School of Mines. My project is titled The Development of a Wireless and Dynamic Scaled Model Shearer for an Optically Accessible Longwall Mine Model. It's part of a larger project to create a scaled longwall mine model. In a longwall coal mine, a shearer translates along the coal face, shaving off coal and rock onto a conveyor belt below. All of this occurs underneath the shields. You can see that in this example video here. The shields create a sheltered area where the shearer can operate without roof collapse, and they leave a crumbling rock zone behind them, as shown in this image. The Caterpillar EL3000 Longwall Shearer is a long cart with raisable shearing drums on its arms to shave into coal faces. It translates along the track and the face back and forth, slowly being progressed forward into the face after each full pass. It is essential to longwall mining, so any accurate model must have an accurate shearer. This project is titled The Design of an Optically Accessible Scaled Version of a Longwall Coal Mine for Investigating Explosion Hazards. Methane propagates throughout the longwall mine, and if ignited, it can lead to devastating explosions. By creating a scale model, researchers can investigate methane propagation at a controllable level and explore ventilation and monitoring options. Thus, the 1/40th scale longwall mine model attempts to simulate the operation of a coal mine at a smaller scale. There are 11 carts in each row, with the front row containing a face module. The front module houses the line of shields and a track to support the translation of the shear, shown by the red line here. The rear gob modules simulate gas flow through the already processed material behind the shields. Because the shear is just short of 42 centimeters long, it can fit on most consumer 3D printers. By printing the shear in PLA plastic, the vehicle is lighter and can be made hollow to fit the electronics. Plus, we can approach higher accuracy to the geometric details and measurements. The shear needs to have an accurate dimensions and shape for an accurate flow analysis using the scale model mine. In order to avoid overcomplicating the model, several computational fluid dynamics simulations were completed to determine how the geometric and dynamic scaling affects the airflow. A distinct difference was found between the simulations of static and dynamic drums, as well as between cylindrical and spiral drums. Thus, the design was decided to include the spiral drums spinning at a dynamically scaled speed. The scale shear needs to match the actuation capabilities of the full-size shear to make the simulation correct. To accomplish this, the shear must be able to raise and lower its arms, rotate its drums at a scaled speed, rotate the cowls around the drum, and translate along the track. The scale model mine must generate accurate airflow data, and thus it cannot leak air. In order to operate within the scaled model, the shear must be entirely wireless, meaning that it has to be able to recharge and receive commands without direct physical interaction. My involvement with the project began in August of 2019. The shear had been mechanically designed and fully developed over the summer, but it was far from complete in operation. The required revisions fell under three main tasks focused on power distribution, drum accuracy, and the finalization of the Bluetooth controls. The first task addressed was the Bluetooth control structure. A previous error in formatting led to an entire redesign of the control structure. The shear, after being turned on, is in a waiting state until it receives commands from its Bluetooth module, which is communicating with the operator's computer through an app called Bluetooth Serial Monitor. A switch case conditional is used to assign an action based on the received command and calls upon different functions. Each function has a specific actuation assigned to it, such as raise arm A or rotate drum B. Finally, a summary of the actuation and a real-time voltage measurement are sent back to the operator's computer. Shown on the right is a chart of character commands and their equivalent operations. And on the left is an example Bluetooth interaction between the operator and the shearer using the Bluetooth Serial Monitor app. The next task was increasing power storage and better manage charging. A SparkFun lithium polymer booster board was utilized to both manage the charging of the batteries and to create a constant output of 5.1 volts for the shearer. The power source used is two 18650 lithium-ion batteries connected in parallel to keep the supply voltage below 7 volts for the booster board while allowing a larger current well to hold charge. Wireless charging and voltage monitoring were additional steps taken to increase the lifespan of the batteries. By keeping a constant eye on the voltage and having charging stations within the shearer's reach, continuous operation is attainable for longer tests. The batteries supply the voltage to the booster board, as shown here, which then supplies constant voltage output to the Arduino and the rest of the circuit. Additionally, the Arduino must be able to read the battery voltage as an analog signal, and wall power, either from an outlet directly or from an induction coil, acts as an input for the charging circuit of the booster board, which in turn charges the batteries. The voltage monitoring circuit is made up of the batteries, a voltage division circuit, and an analog input for the Arduino. The analog input can read the voltage in reference to an external source or an internal source. Because we are measuring the voltage of the batteries, we cannot use their voltage as a reference. So we can instead use the Arduino's built-in 1.1 volt reference. The only stipulation here is that the 5 volts from the batteries must be stepped down below 1.1 volts using the voltage divider. To keep the face module sealed, wireless charging via induction coils connected to constant current circuits can transfer the wall power into the model. The coil is embedded into the track as shown here, and the shearer travels over that track to allow it to charge as shown here. The blue light in the bottom image signifies that the booster board is being charged. The same drums from the full-size shearer can be scaled down in SOLIDWORKS to fit the scale shearer. This accomplishes the geometric scaling details. The rotation system was upgraded from servos that were modified for continuous rotation. The servos used to interface with the I2 serial-controlled PMW board, which controls all of the other actuation of the servos. The PWM board cannot control speed, so to hit accurate dynamic scaling, an L29 3D chip was used to control 2 separate DC motors independently, and thus we can better approach a dynamically scaled speed. This is the final product. There are 2 produced to allow for improvements on one, while the other is used for testing. On the left, you can see a bare circuit attached to the arm assemblies compared with a fully assembled shearer. The actuation is all completed with servos and DC motors. Each arm has servos to change the height and to change its cowl orientation. The drums rotate using DC motors. The track translation is completed with a servo altered for continuous rotation. On this image of a bare circuit, you can see the cowl, the drum, the arm unit, the translation servo, and the PWM board, all hooked up together. This video shows the actuation capabilities of the shearer. This video shows the translational capabilities of the shearer. Although the translation is slow, it is an acceptable speed for the required operation in this model. The scaled shearer is composed of 3D printing and hobby electronics, and yet it plays a valuable role in improving the accuracy of the 1/40th scale model Longwall mine, a project with important safety applications in the mining world. In the future, the shearer needs to be adjusted to have correct drum rotation speed. The correct dynamically scaled speed still needs to be determined. Additionally, the face carts of the model need to progress forward automatically to simulate the advancing of the coal face, and the mechanism to accomplish this still needs to be designed and implemented. This project was made possible thanks to the National Institute for Occupational Safety and Health, as well as my 2 mentors and the project manager.